Our institute is really a materials science institute, understanding of microstructure. We're interested in understanding how microstructure influences the various properties of materials and their functionality, that we take our knowledge from diagnostic input in terms of optimizing materials for specific functions and really looking at the whole value chain of material systems. What's great about Fraunhofer is that we try and make this transition between basic research into application, and we fill that need in terms of addressing materials questions and microstructural questions for industry.
Our expertise covers all kinds of aspects of polymeric reliability within photovoltaic module, and polymers are there to protect the photovoltaic cell against various environmental factors. And we are strongly focused on the method development and establishing a relationship between the polymer formulation and properties and module degradation. We realized that the degradation starts with degradation of additives. That's why we elaborated a new approach, so-called additive to module concept, that relies on a holistic approach, where we start with our own customized development of encapsulant, where we can, in a predefined way, elaborate the formulation of encapsulant or any other polymeric film. And in the reality, we usually have a situation of multi-stressors. That's why we combine all the different factors and test the synergy of these factors on the polymer degradation.
Well, as you know, glasses and glass ceramics are pivotal in our daily life. Cover glasses for smartphones or cooktop panels in your kitchen or windscreens in your car. All of them have different property profiles, and when you do a development of such materials, you need to make those properties fit the application. Fortunately, we have many different techniques at our disposal, including surface analytics, high resolution electron microscopy, also non-destructive techniques like X-ray tomography. What we will be able to use in the near future, using our latest acquisition, TEMSTEM, we will be able to have a look into electron energy loss spectrometry. At the nanoscale, with a monochromated beam, we will be able to do vibrational spectroscopy of glasses and glass ceramics that will help us understand mechanical properties. And that's why we find it fascinating to have an alternative to existing technologies.
Microscopic non-destructive defect localization is a technique that aims at the detection of small electrical defects that are accompanied by heat. We work on several approaches for improving sensitivity and resolution of microscopic lock-in thermography. The first would be the implementation of machine learning, and another approach that we are working on is the development of a semi-analytical approach that allows for the inversion of the heat propagation and, in the end, a quantification and precise localization of defects in three-dimensional space in microelectronic packages. Our partners from industry benefit from these non-destructively operating techniques in the field of technology developments, but also for failure analysis and for quality assessment.
The focus of our group is the assessment of the interaction of dental care products with the oral hard tissue, the dental enamel and dentin, but also the interaction with all biomaterials you have in your mouth, for example, restoration materials or prosthetics or line materials. So our specific capability is that we can investigate efficacy of products at the microstructural level, and techniques that are probably as close as possible to the clinical situation. For example, in our labs we have developed a new technique to investigate chemical and microstructural changes in the human enamel by TOF-SIMS. So this means time of flight, secondary IR mass spectrometry. And this is very valuable to check the fluoride uptake in enamel to develop products with an anti-caries effect, for example. And now the new robotic system we have here at the Institute, we are able to mimic even closer the clinical situation by having the possibility with 3D movements on an entire jaw.
Our research focus is always on sustainable and cost-efficient solutions for our partners. With our unique equipment in Schkopau, consisting of thermoforming, injection molding, hybrid injection molding, and extrusion, we are able to offer cutting-edge technologies for our partners. A great example to showcase our capabilities is the child seat that we have developed together with partners from industries. The material is fully bio-based, and the machinery that we have used to produce the child seat is capable to do the prototyping and also the pre-serial manufacturing. My vision for the future is to establish more and more thermoplastic lightweight structures, sustainable solutions in different applications, like in industries with higher requirements, like the aircraft industry, the automotive industry, or public transportation.
I think that we have societal responsibility in the context of how do we use materials. I think recyclability and circular economy are huge motivations for developing our understanding of materials and providing the best scientific input for industry. This is a huge driving force.